Alright, in this video we're going to be doing explorations with patterns, and in this video we're going to be doing inductive reasoning, arithmetic sequences, Fibonacci sequences, geometric sequences, and other types of sequences. So here we're going to be exploring patterns in this particular video. Okay, now let's look at this particular pattern here. Okay, we got 1 plus 0 times 9, which is 1, 2 plus 1 times 9, which is 11, 3 plus 12 times 9, that's 111, 4 plus 123 times 9, that's 1111, and then 5 plus 1234 times 9, which is 11,111. Now here there are several possible patterns. For example, the numbers on the far left are natural numbers. Right here, these are your natural numbers from 1 through 5. And then the pattern starts with a 1 and continues to the next greater natural number in each successive line. So we start with 0, then starts with 1, and then you got 1, 2, then 1, 2, 3, then 1, 2, 3, 4. And you can guess how this pattern is going to continue. The numbers in the middle are products of two numbers, the second of which is 9. Okay? So the first number in the first product is 0. After that, the first number is formed using the natural numbers and including one more in each successive line. So here, the second number is always a 9. And then those ones, the resulting numbers on the right are formed by using ones and include an additional 1 in each successive line. And in this video, they did leave off a 1 here. Okay, so that should be 5 ones, not 4. And do the patterns continue? Why or why not? Well, the pattern in the complete equation appears to continue for a number of cases, but it does not continue in general. Like for example, if you had this 13 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 9, that pattern breaks down. You're going to end up getting this. So here you can see the pattern breaks down when the pattern of digits in the number being multiplied by 9 contains previously used digits. Okay. Let's first talk about inductive reasoning. In inductive reasoning, we make generalizations based on observations and patterns. Okay. This may lead to a conjecture, and it's a new term called conjecture. It is a statement that is thought to be true, but hasn't been proved. Okay. And it can be proven false by coming up with a counterexample, which is a statement that contradicts the conjecture. For a counterexample, you want to find one example that is going to be false for that particular statement. Okay? And here's the danger of making conjectures. You want to choose points on a circle and connect them to form distinct non-overlapping regions in this figure. 2 points determine 2 regions. 3 points determine 4 regions. And 4 points determine 8 regions. What is the maximum number of regions that would be determined by 10 points? And as you can see in this particular figure, you see you got 2 points and 2 regions. Here you got 3 points on this circle, and you got 1, 2, 3, 4 different regions in that circle. And then you got 4 points. Connect all 4 points in all the possible ways. You're going to come up with 8 regions in this particular situation. And it appears that each time we increase the number of points by 1, we double the number of regions. If this were true, then for 5 points, we would have 2 times the number of regions with 4 points, or 2 times 8, which is equal to 16, or 2 to the 4th power, and so on. So if we base our conjecture on this pattern, we might believe that for 10 points, we will have 2 to the ninth, or 512 regions. An initial check for this conjecture is to see whether we obtain 16 regions in 5 points. And here's that circle with 5 points, and we connect all the points in all the possible ways. There are, in this case, 16 regions in that circle. But for 6 points, we would expect, based on that pattern, to get 32 regions. Now, if you look at this, we only came up with 31 regions. So here, this is an example of how to come up with a counterexample. We come up with one example that would show that a particular conjecture would be false. And in this case, we were predicting from the pattern that for 6, that would be like 2 to the 6 or 32. But actually, it's 31. So that conjecture is not true. Okay. Now let's look at what a sequence is. It is an ordered arrangement of numbers, figures, or objects. And sequences can be classified by their properties. One of them is an arithmetic sequence, which is a sequence in which each successive term is obtained from the previous term by addition or subtraction of a fixed number, and that's called the difference. Some textbooks call it the common difference when you're dealing with an arithmetic sequence. Like in this example, the sequence 2, 5, 8, 11, 14, and so on, that is an arithmetic sequence because the difference between each term is 3. In other words, you're adding 3 each time. You start off with 2. If you add 3 to the 2, you're going to get 5. Add 5 to the 3, you're going to get 8. Add another 3, you're going to get 11. Add another 3, you're going to get 14. Okay, look at this example. You want to find a pattern in the number of matchsticks required to continue the pattern. Note that the addition of a square to an arrangement requires the addition of 3 matchsticks each time. So in this case here, the numerical pattern obtained would be this. You have 4, and then 7. This one has 7, so if you count here, you'll see that there are 7 matchsticks here, forming 2 squares. The next one is 10, then 13, then 16, 19, and so on. Here, this is another example of an arithmetic sequence with a difference of 3. Find the first 4 terms of the arithmetic sequence given by a sub n is equal to 4n plus 3, and determine whether the sequence seems to be arithmetic. Okay, so here, this first column is the number of terms. That's 1, 2, 3, and 4. In fact, that's what n is going to be. N is going to be 1, so you got 4 times 1 plus 3. 4 times 1, that's 4 plus 3 will give you 7. N is 2, so here 4 times 2 plus 3. 4 times 2, that's 8 plus 3 is 11. N is 3, so 4 times 3, that's 12 plus 3 will give you 15. And then for 4 times 4, that's 16. 16 plus 3 is 19. So in this case here, this sequence seems to be arithmetic because the common difference is 4. Between 7 and 11, that difference is 4. From 11 to 15, that difference is 4. From 15 to 19, that difference is also 4. Find the first 4 terms of the sequence given by a sub n is equal to n to the second minus 1, and determine whether the sequence seems to be arithmetic. So here, this time, if we let n equal 1, that means you're going to have 1 to the second power. We do the exponents first. 1 to the second, that's 1. 1 to the second, of course, that means 1 times 1. 1 minus 1 will give you 0. If n is 2, 2 to the second, or 2 times 2 is 4, minus 1 will give you 3. If n is 3, 3 to the second, 3 times 3 is 9. 9 minus 1 will give you 8. N is 4. 4 to the second is 16. 16 minus 1 will give you 15. Now, as you can see here, this sequence is not arithmetic because there is no common difference. From 0 to 3, that difference is 3. From 3 to 8, the difference here is 5. And then from 8 to 15, that difference is 7. So the common difference does not exist here. So this is not an arithmetic sequence. And the diagram in the figure below shows a molecular structure of alkalines. A class of hydrocarbons called C represents C represents a carbon atom and H represents a hydrogen atom. A connecting segment shows a chemical bond. And one remark is that CH4 stands for C1H4. And you can see the figures for each one of these. The molecular structure of methane, ethane, and propane. Hectane is an alkaline with 100 carbon atoms. How many hydrogen atoms does it have? You first study the drawing of the alkalines and disregard the extreme left and right hydrogen atoms in each. With this restriction, we see that for every carbon atom, there are 2 hydrogen atoms. Therefore, there are twice as many hydrogen atoms as carbon atoms plus the 2 hydrogen atoms at the extremes. What do I mean by that? Let's go back to that. Okay. Ignoring these extremes here, for every 1 carbon atom, there are 2. In this case, ignoring these, we got 2 carbon atoms, so now we got 4 hydrogen atoms. And ignoring these hydrogen atoms on the ends, we got 3 carbon atoms, but here 6 hydrogen atoms. So that means, in this case here, there are twice as many hydrogen atoms as carbon atoms, plus the 2 hydrogen atoms on the extremes. So this can be summarized as follows in this particular table here. So for N, it will end up being 2N plus 2, because that's twice the number of carbon atoms, then plus the 2 hydrogen atoms on the end. Another example would be a theater is set up in such a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. The last row has 144 seats. How many rows are there in the theater? Okay, so now, the first row has 20 seats. That's A sub 1. That's going to be 20. A sub n, which is the last row, that's 144. The D, which is the common difference, because there are 4 additional seats, so D is equal to 4. And this is the formula that we use for finding the nth term of any arithmetic sequence. A sub n is equal to A sub 1, which is the first number, plus n, which is the nth term, minus 1, multiplied by D, which is your common difference. Okay? So that's the formula that we use to find the nth term of any arithmetic sequence. Okay, now what we're going to do is use this formula to replace these given values here. A sub n, that's 144. And that's going to be equal to A sub 1, that's 20, plus n, that's what we're trying to find, the number of rows, minus 1, close parentheses, times D, that common difference is 4. Now, if we simplify this, we need to subtract 20. That would be 124. We'll subtract 20 from both sides. That would give you the 124. That's equal to n minus 1 times 4. Divide both sides by 4, you're going to get 31 is equal to n minus 1. Then add 1 to both sides, you're going to get 32. So here there are 32 rows in the theater. Okay, so this is how we can use this formula to find the nth term of any arithmetic sequence. Also, we can use that to find out what n is. Another type of sequence is the Fibonacci sequence. The Fibonacci sequence is defined by this: f sub n is equal to f sub n minus 1 plus f sub n minus 2. In other words, and this is going to be for n is equal to 3, 4, and 5. In other words, this is what a Fibonacci sequence is. You have to be given two numbers to start off with. You're going to take the sum of the first and the second numbers to get the third. Then you add the second and the third to get the fourth. In other words, the next number is going to be the sum of the two numbers that comes before it, like in this case here, 1, 1. Now to get that third number, you have to add 1 plus 1, that's going to give you 2. The next number is going to be 2 plus 1 will be 3. And then the next number will be 3 plus the 2 will be 5. The next number is 5 plus 3 will give you 8. And this continues on and on and on. Because to get the next number, you add the two numbers that come before. So if I want to find the next number after 144, I will add 144 and 89 together. And that will give me 233. So the next number after 144 will be 233. Now the sequence is a geometric sequence. And that's a sequence in which each successive term is obtained from the previous term by multiplying a fixed non-zero number, or in other words, the ratio. Like in this case here, the sequence 2, 6, 18, 54, 162, and so on, that is a geometric sequence because the ratio between each term is a 3. In other words, if I start off with 2, multiply that by 3, I'm going to get 6. Multiply the 6 times the 3 will be 18. 18 times 3 will be 54. 54 times 3 is 162. And if n is a natural number, then n factors means this. A sub n is going to be, a sub n, is equal to this. A times A times A all the way to times A. N factors means that your n is going to be your exponent. That means that A is going to be used as a factor n times. So in this case here, let's say I had 5 to the 4th power. That's 5 times 5 times 5 times 5. That exponent of 4 tells me that 5 is going to be used as a factor 4 times. So it'll be written like this. It's not saying 5 times 4. 5 to the 4th means this. That exponent tells me how many times the base is going to be used. Okay, now this condition works if n is 0 and A is not equal to 0. This is another case. N is 0, A is not equal to 0. A to any number to the 0 power, with the exception of 0, will be 1. Okay, A to the 0 power is 1. Which means, for example, 6 to the 0 power is 1. 10 to the 0 power is 1. 158 to the 0 power is 1. Any non-zero number to the power of 0 is automatically going to be 1. Okay, next, these are other sequences. One of them is figurative numbers. Those are sequences of numbers that can be represented by dots or arranged in the shape of geometric figures, like this one. Start with 1 dot, and then 3 dots, then 6 dots, and then 10 dots. These are called triangular numbers here. And then you got your square numbers like 1, and then 4, then 9, and then 16. Okay? Look at this example here. Here you want to use differences to find a pattern, then assuming that the pattern discovered continues from the 7th term in that sequence. So here you're starting off with this: 5, 6, 14, 29, 51, and 80. Now if you find the difference between 5 and 6, you're going to get 1. The difference between 6 and 14, that's 8. The difference from 14 to 29 is 15. From 29 to 51, that difference is 22. Then from 51 to 80, that difference is 29. Okay? So there's no usual consistent pattern there. So we keep going. From 1 to 8, that difference is 7. 8 to 15, that difference is 7. 15 to 22, that difference is 7. 22 to 29, that difference is 7. Okay, so here the first difference in it is an arithmetic sequence with a difference of 7. So the sixth term in the first difference row will have to be 29 plus 7, which will be 36. So here if you add 29 and 7, that's going to be 36. So the seventh term in that original sequence will be 80 plus the 36, which will give you 116. Okay, so that seventh term in that sequence is 116. Okay. All right, and that will conclude this particular video on sequences and patterns.